Hi, everyone, and welcome to a detailed overview of DEXTER. Named entity recognition is usually developed and tested on text from well-written sources. But in the case of intelligent voice assistants, where NER is an important component, speech recognizers often make mistakes. For example, detecting Play Bohemian Rhapsody as Play Bohemian Raspberry. Users could make mistakes, such as calling Cristiano Ronaldo Cristiano Nando. And entity labels could depend on non-textual properties like popularity. For example, Moana could refer to both an album and a song. The goal of this work is to design an NER system that is robust to noisy spoken natural language utterances and that encodes non-textual properties of entities such as relevance and popularity directly as a part of model training. Some of our contributions include proposing a novel method of encoding external knowledge about entities as part of NER model training, treating entities as objects with attributes and encoding these through a neural network to enable NER models to learn correlations between input tokens, attributes of entities that these tokens belong to, and their true class labels, demonstrating that our framework can perform significantly better than NER models trained only using word and character embeddings, or NER models using other implementations of gazetteer features. And we also show that our framework can empower other natural language understanding tasks like semantic parsing. Coming to our method, here I'll first give an overview of the method itself and then walk through a detailed example. We incorporate external resources. We do this by conceptualizing entities as objects that have various document properties associated with them. To construct the properties associated with entities, we crawl a knowledge graph that is updated daily, which gives us our universe of entities. From text descriptions associated with nodes and the relations they take part in, like incoming and outgoing edges in the graph, we construct token n-grams that may be used to refer to the entity. We augment these n-grams with aliases and acronyms mined from various sources. For example, San Francisco International Airport can also be referred to as SFO. To construct properties associated with entities, we create an inverted index from these n-grams to entities and compute and store TF-IDF scores for all n-grams. We also compute and score a popularity score for each entity based on the frequency of occurrence of these entities in anonymized usage logs. This gives us a list of around 10 million entities with their associated properties. Now, we efficiently search for candidate entities given an n-gram of tokens. We make the search robust to ASR and user errors by training a corrections model learned from common usage patterns. For example, Cincinnati Bengals then gets corrected to Cincinnati Bengals. Coming to an overview of our dense aggregation layer. For every token T in the utterance, where T goes from 1 to the length of the utterance, and for every n-gram N that token T is a part of, we search for the candidates. Every token is at most a part of 6 n-gram searches: a unigram, a left bigram, a right bigram, a left trigram, a center trigram, and a right trigram. When searching candidates for every n-gram, we search for every entity class in our ontology. To encourage the model to use contextual information, we incorporate a layer of 1D convolutional neural networks on top of the dense aggregation layer. This layer allows each token to have a contextual representation that includes features from neighboring tokens. This layer can learn complex dependencies between tokens other than the current token and across different entity classes. And finally, our CNN adds 2 important inductive biases: location invariance and edge detection. Let's run through this with an example. Consider an utterance. What year was whatever happened to baby Jane made? For a given token baby, we consider the unigram which the word baby occurs in. We consider both the left and the right bigrams, which will be to baby and baby Jane in this case. And we consider all three trigrams, happen to baby Jane, and baby Jane made. For each of these n-grams, we do a search within entities in our knowledge graph corresponding to all the different entity types. For example, for the unigram baby, we might retrieve the artist baby, among others. Likewise, we might retrieve the song newborn baby sleep. Similarly, we do a search on the bigrams and the trigrams. Each retrieved candidate has a topicality or a TF-IDF score and a popularity score associated with it. We concatenate the TF-IDF scores of the entity across all the n-grams, indexing it, along with the popularity score of the entity to get a vector R. Here, OC transpose is a one-hot vector with a 1 in the location corresponding to the class of this entity, and we multiply OC transpose by R to get a matrix, which we then flatten. So we effectively get a vector in which a chunk, which is decided by the class of the entity, is filled in with this vector R. And R contains the TF-IDF scores and the popularity. The rest of the entire vector is filled with zeros. We then pass each of these entity vectors into a shared linear layer to get S sub E sub I, which is a single scalar output per entity. The output so obtained is a vector, one for each token, that has a length equal to the number of entity classes supported in our ontology. This vector is obtained by a reduction, where we put in the corresponding position of the vector the highest score that any entity of that class got for that particular token. We then convolve on the output of the aforementioned dense layer with a 1D class-specific convolutional neural network to get our final output. Our NER module uses a sequence tagging model. The model architecture for the NER component is a classical sequence tagging model, which assigns a BIO label for each input token. The model is based on an architecture from Lampel et al. 2016, where they first send the sequence of characters through a character embedding layer, and then concatenate the character-based representation with a pre-trained word embedding representation, and pass this through a bilistium encoding layer, and then feed this representation into a CRF to predict the final label. For our extended system, we concatenate our DEXTER embeddings to the word and character embeddings before feeding this combined embedding to the upper layers. The weights that contribute towards DEXTER are learned end-to-end during training. The shallow semantic parsing task involves jointly identifying the user's intent and assigning a semantic label to each word in an utterance. For example, in the movie Play Moana, the model identifies the user intent as play, tags movie as the type of the entity to be played, and tags Moana as the name of the movie. Unlike NER, the semantic parsing is domain specific, with each domain having a different set of intents and semantic labels. Further, we are not looking at for units above the word level. The semantic labels are assigned to every word in the utterance and are not only for named entities. For this task, we compare against a model that uses a bilistium with word embeddings and gazetteer features as input, with a baseline showing performance without gazetteer features. We compare these settings with a version replacing the gazetteer with DEXTER. As in the case of the NER setup, we train the DEXTER embeddings and the model end-to-end. Coming to our data was randomly sampled from around 500,000 unique anonymous English transcripts that were machine transcribed. We used a 70-20-10 train depth test split. We used 3 popular domains that are named entity heavy: music, sports, and movie and TV. And we have 23 fine-grained classes like song, artist, celebrity, athlete, and so on. So for our results, we use the standard NER F1 metric, as in the Cornell 2003 shared task, which requires an exact match of both the span boundary and the type. For shallow parsing, we use token level classification accuracy. Our baselines include Lampel et al. 2016, which uses word and character embeddings with the bias scheme and CRF. We also compare against Liu et al. 2019, which is like Lampel et al. 2016, but with a gazetteer enhanced sub-tagger that uses token embeddings in our case, and performs a soft dictionary matching to generate gazetteer embeddings, which are then concatenated to the input word and character embeddings. We also compare against Stratonov and Roth 2009, which is Lampel 2016, but with the token match gazetteer features concatenated to the input word and character embeddings. And Peshteliev et al. 2020, which uses self-attention and match span encodings to build enhanced gazetteer embeddings, which are then concatenated to the input word and character embeddings of Lampel et al. 2016. As can be seen from the results table, our proposed approach consistently outperforms all of our baselines on all 3 domains on the NER task. Here we present an ablation to show the utility of each of the different modules in our proposed approach. In the second row, we replace our single layer perceptron with a simpler max pool layer. In the third row, we replace our class specific single layer perceptron with a single shared single layer perceptron, independent of the entity class. In the fourth row, we replace our class specific CNN with a single shared CNN that is independent of the entity class. And in the last row, we show the utility of the CNN by removing it altogether. In each of these cases, we see a drop in the performance over our overall architecture shown at the top. In semantic shallow parsing in a voice assistant setting, using DEXTER improves over baseline models trained both with and without a token match gazetteer feature. This happens in 9 out of 11 domains in our test sets, with statistically significant improvements in 5 of them. We see a 5.4% reduction in error rate averaged across all the 11 domains over the model without gazetteers, and an improvement of around 3.1% over the model, which also uses token match gazetteers. Coming to a few qualitative examples. For find I know you did last summer, without DEXTER, no exact matches are present, and NER is unable to identify a named entity. But with DEXTER, it's a popular movie with a high TF-IDF score, so NER correctly identifies the span and type, thanks to the entity I know what you did last summer. Likewise, Godzilla is a very popular movie franchise and a popular song by Eminem. So for Play Godzilla with DEXTER, NER is successfully able to disambiguate based on signals like popularity and freshness. For the song, but for the utterance Play the Song Godzilla or Play Godzilla by Eminem, with DEXTER, NER continues to respect semantic context over other signals. In conclusion, we proposed a novel method of encoding external knowledge about entities as part of NER model training. We treat entities as objects with properties and encode these entities through a neural network and use features such as popularity and relevance. Our work is targeted towards noisy natural language utterances, and our framework is robust to speech transcription and user errors. It's also particularly useful in scenarios where named entity label is heavily influenced by current interests and trends. Finally, feeding DEXTER embeddings into other language understanding tasks, such as semantic parsing, substantially improves the accuracy of these models as well. Thank you.